Hi, good evening. So on my next slide, it'll actually say the 19th of January 2025. I have gone a slightly early, it is the 18th of January 2025. But there's not much business to be done on a Saturday evening, so it's a good time to make a video. So with that said, let me go forward. So we do this weekly webinar. It's always answering technical questions that have come in through the week. I think there's actually some fairly technical stuff. Not much maths tonight, but definitely technical questions. And I'll essentially jump straight into the questions. So somebody's very interested in using gold or custom gold PCBs for making biosensors. I will comment on that. This is something I have been talking about at least, I would say, 10 years. My first experience with using PCBs for biosensors was probably about 15 years ago. I'll talk about geometries of screen printed electrodes. I've got a couple of screen printed electrodes actually in front of me. Later on I'll do a bit of a demonstration. One of them is circular, one of them is rectangular. People think that the kind of design of these electrodes is really significant. It's really not actually that significant, and I'll show you just by doing some science in front of you. So I've got a potentiostat in front of me. The nice thing about the ZP webinars, it's not talk. I do have some potentiostat here. I've got a couple of screen printed electrodes. I've got some test solutions. This will be the first one I use, so you'll see me do some testing shortly on the sensor or potentiostat. Alright, so we'll talk about gold screen printed electrodes. We'll do voltammetry. Question number 2 and question number 3 sort of slightly overlap. And I'll also talk about glucose in sweat. Somebody was kind enough to ask some questions last week. They came back and asked some more questions today, and I will answer them. First thing I'll say, glucose in sweat is hard. Glucose in sweat on an academic budget when you're just one person, that's a very high lift. So I think if I talk about it this evening, I'm only going to be describing technology readiness level number 3, TRL 3, to make something wearable that's really robust. Don't forget BioLink in San Diego. They're making a wearable biosensor at the moment, admittedly using microneedles, but they've raised 154 million in the last 4 years. So glucose on the body, whether it's sweat or transdermal, very tough, very expensive project to do well. I'll talk about Genistein, which is a marker really whether there's soy in food or not. So I'll do a quick demonstration as well. So there's quite a few demonstrations this evening and these technical questions. So PCBs, geometries of electrodes, a couple of voltammetry experiments, in part to answer a question and in part to illustrate geometries of electrodes, glucose and sweat, and then also a demo at the end on food detection. We do have in-person workshops. There's going to be one in the 22nd and 23rd of January. Just FYI, any links you see in these videos, I'll put them in the links underneath the afterwards as well. Question number 1 is about PCB, printed circuit board for gold. They've got a certain design. I've only taken a tiny segment of their design. The first thing about this, and this will probably be their electrodes here, the first thing is people go for things like PCBs, printed circuit boards, and screen printed electrodes. People go for these kind of materials because they think in the R&D phase it will be low cost. But in the R&D phase where you're doing your basic science and your production runs are very low, it won't be low cost. No matter what route you take, you'll end up paying the price, and you'll end up paying the price either through lots of iterations, or you'll end up paying the price because ultimately it didn't work, or you'll end up paying the price because actually you had to put in the hundreds of hours in order to actually make it work. But I'll talk about PCBs. But I just want to kind of say that whether you're going PCB route or screen printed electrode work, don't assume that these things are low cost. They only become low cost when you're producing millions of products per month. And so people say, oh yeah, well, PCB, printed circuit boards, these are low cost. Well, they may be for the electronics industry, but when you try to use them in biosensing, it's not low cost. There's a lot of effort trying to make printed circuit boards, gold printed circuit boards work for biosensors. Most of the time, if people are like doing voltammetry on a printed circuit board and the electrode is gold, they'll actually find out at some point the current goes really high. Here I've sort of shown the current going high and it kind of flatlining. Now, what I'm trying to illustrate here is actually what happens most of the time with this kind of stuff is you've got this kind of gold and it all looks very pristine and lovely, you know, and you think, oh, great, you know, I'm going to tick the box, low cost, easy to manufacture, electrodes made out of printed circuit boards, but you use them one time and you get this corrosion event. And I'm pretty sure that, you know, people will have come to us because they've been everywhere else, and then they're kind of, you know, they know what I'm saying when I talk about this corrosion events. You get basically pitting currents. And this is because printed circuit boards are designed for the electronics industry. They weren't designed to get wet. And obviously with biosensing, I know, you know, you'll know this because I'm about to do a demonstration where I'll actually add some solution to this. But, you know, stuff gets wet, and that wetness, the materials in a printed circuit board weren't actually intended for this application. So I'll talk about it. I'll tell you that this person hasn't explicitly told me that they've got this problem, but I can explicitly tell them, if you haven't got it, you will get it. It's sort of a well-known, well, maybe it's well-known on the ZP, let's say, YouTube channel, but outside of that, there's not actually much discussion of it. Now, the reason that you get this corrosion problem when trying to use PCB gold for biosensing is because underneath the substrate, you've got this kind of FR4 substrate, that sort of green material. You've actually got some copper, you may have some electroless nickel, and then on top of that, you might have gold, which also has nickel in it. So already you're starting to discover that actually these are not really gold electrodes that you're getting actually from the PCB, guys. They're actually gold mixed with nickel. So there's the start of your corrosion problems. And then as soon as you put some sort of potential on them, you start getting this kind of corrosion, and that's when you kind of get these pits here, and you get a really massive current, and you know, you're not going to get any useful electrochemical data out of that electrode. Now, people think, oh, I'll fix this problem by actually just making this gold thicker. I'll just go around and I'll ask a few vendors to make it thicker. It doesn't work. You have very little control over those vendors. Those vendors don't actually have that much control themselves. There are very significant companies that have put very significant amounts of money into fixing this problem. So you can try and thicken this up to a few microns, but I really suspect that it's still going to happen and you're still going to get this corrosion current. The only people I really think have solved this problem is actually massive sensors. Now, the thing I would say is before you dive in and start requesting bespoke pieces off people, you're better off actually just testing their standard pieces. So massive sensors, I'll put a link to that, is a good place. They can do bespokeness, but you want to check that you can do your chemistry on their gold PCB. But they're the only people who really put the correct amount of effort and have the correct IP in place to actually use gold PCB as a biosensor. So I'll put a link to those guys. You can also just think as well as you know, why am I using gold PCB? I can understand why people do it. They like the kind of attractiveness of it. It makes for publishing paper. I mean, you can also just try screen printed electrodes as well. Screen printed electrodes don't suffer from the electroless nickel and copper vulnerability that's with gold. So these PCBs, these gold electrodes that I'm linking to here, these are from ZP. These will be perfectly robust enough. Again, it's probably best purchasing standard products before you try going bespoke. People go, I want bespoke. No, you've got to make sure that these vendors' material sets are actually useful before you go there. So you can at least do that with Massius because you can just buy a standard part of them, and you can do the same with ZP as well before you do go bespoke. Main problem with bespoke electrodes is that people want to have an expectation that, you know, they have an expectation that things are going to be low cost. And I sort of started this webinar, I should say, and saying, you get low cost when you have high volume manufacturing. There's a fundamental problem with bespokeness in the R&D phase. The fundamental problem is you do not have high volume. And so getting low price is hard because you do not have high volume. You're the only person consuming those material in the world. And yet you will go out there and find somebody to do it for you low cost. As soon as you bring it back in, you put a solution on it, you apply a voltage, bang, corrosion current, it's all over. So you didn't actually get a low price. You just got something that looked beautiful, but it didn't work. And that's what's going to, essentially, that's what happens a lot. So the quality is not met. And you know, the idea of thickening the gold, I mean, these ideas have been tried. I have seen this tried at least starting 15 years ago. It's not just as simple as put more and more gold down. As it is, once you start putting more gold down, you're then asking the fabricator to go outside of their normal operating conditions, and it becomes expensive. There's a fundamental sort of disconnect between quality and price. People want a high quality, but actually what they really want is a high quality but at a low price. And there's only one way, that's very, either somebody's giving away something for free or cheap, which, you know, that is just bad business on their behalf, or you can have high quality and low price by having high volume manufacturing. But there's the catch. I want a bespoke piece. Therefore, by definition, it's not high volume. You know, you may only want 500 pieces, which is not high volume. So therefore, you don't have high volume. So you want high quality and a low price. But high quality and low price only comes with high volume manufacturing. So if you have a low price, you'll end up with low quality. It's a triangle, essentially, between quality, price, and volume of manufacturing. Now with ZP, we can get to a high price. We can get to a low price and high quality because we're doing high volume manufacturing. You know, so at ZP, I'll talk about, you know, our electrodes this evening, but we actually, you know, we are only way we can actually make these electrodes work and have high quality and a low price is by doing high volume manufacturing. Again, when you have a bespoke piece made, you may think that I'll have 500 pieces. That's really not high volume. It's not manufacturing. It's just a bit of fabrication, and you will have a problem with quality, especially because you will have a restriction on your budget. Now at ZP, we can again do these low prices because why? Because we do high volume manufacturing. The high quality means that we end up actually being able to do assays on top of our electrodes, and you'll often see that our assays have no calibration. And why do they have no calibration? Because there's a really important part of quality. The quality that I've talked about so far is, you know, gold PCBs have a vulnerability. That vulnerability is as soon as you put a solution on them and you put a potential on that electrode, you'll start getting corrosion. And then there'll suddenly be a very high current. You get a lot of corrosion of the nickel, the copper, maybe the chromium underneath that gold. There's another problem with quality when it comes to bespokeness, and that's reproducibility. You're going to find this when you start getting the pieces. Now at ZP, the only way we can have reproducibility as part of our quality set is because we're actually manufacturing in high quantities and we do a lot of testing. So be careful with bespokeness. You can definitely get people to make you bespoke electrodes, be it screen printed, or you can get people to make you bespoke pieces, be it PCB. But you will struggle, and it won't really become high quality until you launch a company, you make the investment, you put the quality systems in place. Then you may get, then you may be able to essentially get low price per piece, but overall it's because you're actually producing millions of pieces. Now the reason again that we can do high quality and low price is because actually we are able to sort of feed that R&D market with, you know, I don't know how many tens of thousands of these we're shipping nowadays, but you know, we are shipping a lot of these screen printed electrodes. So be careful with bespokeness, because bespokeness feels like you can publish papers, etc. I get it, you know, and you want to make a wearable or something like that, but it does have a problem that you'll go around, you won't have much budget, you will find vendors that will do it, but what they'll never do is guarantee the performance, because they won't understand the question about the performance, and when you do put a solution on there and apply a voltage, you will get a corrosion current. So the reproducibility, and then you also find that they're not reproducible, and some of them will fail and some of them won't fail, but you'll find actually a real problem with a failure. And what we're doing actually at ZP is producing in high volume and doing a lot of testing and making sure that our reproducibility is really good. The biggest problem that's holding back a lot of electrochemical biosensor development is actually the reproducibility of the electrodes. But reproducibility really can only come from having a quality system in place. And a quality system in place, like ZP is ISO 13485, it costs us hundreds of thousands of euros per year or dollars per year to maintain just a quality system, let alone adhering to it. but the documentation, all the processes are in place. It's a lot of money to have a quality system in place, but that quality system means that we actually do have a really good reproducibility on our screen printed electrodes. And then we can actually develop assays on top of the screen printed electrodes very rapidly. Now, slight change of direction now. So that whole conversation was really about somebody wants to make biosensors out of PCBs. They probably already know, though they haven't told me, that there's actually a corrosion problem with PCBs. I've talked about it's not enough just to actually thicken that gold. You can try it. I've honestly seen people trying this for 15 years. Either just change material sets altogether and go for screen printed electrodes, or try out biosensors as well. But don't go in there asking for bespokeness. Go in there asking just to test some of their standard products. Now, what I'm going to do now is talk about electrode geometry. So I've got a couple of electrodes in front of me. I've got one of these circular electrodes. You'll see me do a test on this, so wait on to watch the rest of the video, and you'll also see me test one of these rectangular electrodes. Now, I'm glad that I've been asked this question, actually, because it's something I've known, but now I can kind of get to point. The nice thing is I've got the Potentiostat here, the Sensi or Potentiostat. I think this is one of the world's most elegant Potentiostats, and I'll do a demonstration with it in a minute. But people are concerned that the geometry of a screen printed electrode. Now, these electrodes are on the kind of millimeter scale, so you could consider them macro electrodes. Now they're concerned that, not concerned. Many people, are not concerned, but you can sort of you can read the literature and think, oh, corners. I'll get what's called an edge effect or corner effect. Now, what I mean by that is, if I took an electrode, a planar electrode like this, on the sort of millimeter type scale and bigger, I'll have what's called planar diffusion here on the sort of face of this electrode, and on the corners and on the edges I'll have hemispherical diffusion like this, and that kind of is a more efficient diffusion. So effectively you could argue you've got more current on those edges and those corners than you do on the planar part. Now, as that electrode shrinks down, the contribution from the edges and the corners actually increases, and if you decrease a bit more, then the contribution, or the relative contribution I should say, from the edges and corners increases. So you could kind of argue that at some point, well, and this is when you get to a microelectrode, that a microelectrode does have hemispherical diffusion, has a very efficient diffusion. Now, to get that kind of microelectrode, you need to really be 10 micrometers or 1 micrometer, that kind of scale. You're not going to see that kind of scale necessarily in the hundreds of micrometers, so that hundreds of micrometers is acting like a macro electrode. When you get down to 10, 1 micrometer, then you're starting to act like a micro electrode. But people would still think, oh, well, these edges, these corners are actually going to give me significantly different signals than, if I compared it to the circular electrode. Because I'm sort of illustrating it here, the idea that you've got this hemispherical diffusion on these corners and edges. The shocking news is it's really not it's really not a process or a phenomenon that you actually witness. Now, I'm going to do a demonstration in a minute, but what I'm going to do is, that was question number 2, when I was sort of saying we have these different designs because they fit with different customer needs and our needs as well. And actually, the different geometries really make no difference to the signal. And that's actually the bit that will surprise people. And I'll demonstrate it by doing a demo. But I'm actually going to do the demo by combining it with question number 3. Because question number 3 is using a Sensi All from ZP. I'll discuss their voltammetry. So they've got some voltammetry that looks like this. It almost looks nice. They've got an oxidation and reduction wave. But they've got this sort of massive amount of capacitance as well, and it's no criticism of them. They're perfectly nice people and they're perfectly good scientists. It's just they were very kind and also shared me a screenshot of their instrument setup. And what it is they're doing a scan rate at 1,000 millivolts per second. So with electrodes, the slower you scan, the higher the total current is from what's called the Faradaic processes. But as you increase the scan rate, you start increasing the capacitance effect. So in fact, they do have a nice voltammetry here, but there's so much capacitance because the scan rate is at 1,000 millivolts per second. So if they turn that down a bit, now turn it down to 10 millivolts per second, you'll get really beautiful cycle voltammetry. Now I'm going to do a demonstration in a minute. I'm only going to do it at 100 millivolts per second, but I'm deliberately doing that because otherwise this will take it'll be a long, boring video. So I'm going to do a demonstration where I'm going to say, okay, I'm not going to do it at 1,000 millivolts per second. I'm actually going to do it at 10. So this is just to remind me. So what I'm going to do now is change to here, external camera. I will grab a pipette tip. Now, just know I'm doing this live recording. So what I'm doing now is going to my phone, and I should have thought about this earlier on. Right, I'm going to my phone. I'm just going to open up the app, which I'm doing. I'm just going to log in, which I'm doing. Right, so I've logged in now. I just want to go to cyclic voltammetry. You may see me do this cyclic voltammetry a few times as I get the parameters right. Whoops, daisy. Just going to scan, connect. Now I'm just going to scan here. Yep, cyclic voltammetry. Okay, so I've got cyclic voltammetry. Now I need to give it a name, which I should have done all before. This will help me find the data later on. Demo. Whoops, daisy. I'm using one of our 303s. 303. I'm using it with ferricyanide. And I'm probably doing it 5 millimolar. Okay. So I've did all that a little bit quick. So forgive me if I kind of make an error on the first run of it. I'm just going to take a pipette. One of the things I love, pipette tip rather. One of the things I do love, and I do say a lot about electrochemistry, is, oops, daisy, oh good, there is some solution in there. Doesn't need much sample, and that really does lend itself to rapid test. If you don't need much sample, it's much quicker to prepare samples. Very good for the food industry, very good for the medical industry, especially the medical industry where people don't want to give you much blood. But I'll just put the 50 microliters on here. And I will go, I'm just thinking aloud a little bit. Continue. Oh, I've got to do this again, yeah. Let me just do this quickly. Like I say, this is essentially a live demo. And I will almost do it. Just give me 1 second. Right, sense it all. Log in. Oh, right, log in. Cyclic voltammetry, connect to the device, good. Right. Demo. Right. 303 and ferry and 5 millimolar. Right, good. Continue. Right. I've got my settings here. I'm just going to set the current range a bit higher. I might even set it that high. I'm going to do what I'm going to do just to do this one. I'll start at minus 200 millivolts. I'll go to 600 millivolts. I'll do 100 millivolts per second to get nicer CVs. I should actually drop that down a bit. But 100 millivolts is nice and fast. One repetition. I set the current range quite high actually on this, and I'll start measurement and it will record it. Like I say, I'm doing all that quite quickly, so if I make any errors, I sort of apologize for it. So I can see it gathering the CV in real time. I realize that I'm just going to go, see me looking at another screen. It's because what it'll do is it'll record that CV and then it actually just saves it to the cloud, which I think is a really neat feature, because there's one question that academics can ask their students is like, where's my data? Well, this is gone, it's recorded it live. Now I can, whoops it daisy. I'm sorry, I'm just thinking aloud a bit. I'm just going to share my screen, which I'm going to do here. Go in, find my data. In fact, there it is. Whoops a daisy, yeah. and I can see my CV up in there. Now the reason I'm doing this is because I want to sort of demonstrate to you that, you know, that was a rectangular electrode. It just gathers, because I was doing a quite fast scan rate on a carbon electrode. You know, it's not the world's nicest CV, but it doesn't really matter what the shape is. And the reason I can kind of make that comment is, let me do a slightly different experiment for you now. So what I'll now do is I'll just take this out. I'll put it in the circular electrode. So a very different geometry. We call this the 505. Is it the 505 or the 501? 505 might be a freeway in the US. I'm in California, so my apologies if I'm mixing up there. Right, so I've got the electrode in there. I've got my solution. I'll just take that. I'll put it on there, which I've done. I'm just going to go done. I'm just going to give it a name so I can find it. It's called the 501, not the 505. The 505 is a freeway in California. 501, done. Continue. Same settings. So, if in answering question number 3, the person's got a very capacitive looking signal, and it's not a criticism there, it's just the settings are at 1000 millivolts per second, so that's like 1 volt per second. That's really kind of fast stuff, and that will give you a large capacitance. I'm doing these ones at 100 millivolts. I don't have these massive capacitances. Again, upload complete. I really like the system because there's nothing worse than, you know, being a PI, a principal investigator at a university, or being a CSO, a chief scientific officer at a company, and not knowing where the data is. And I always know where the data is with this system because, remarkably, it's up in the cloud. So let me just go over here and do a quick refresh and go to here. And then I can see my signal up here, a little distorted, but it's not, I'm not getting significant differences really between these two electrodes. So for me, this idea about the diffusion being significantly different between circular electrodes, and I'll get, circular electrodes and, how do I say this, rectangular electrodes, you really don't see much difference in the signals. What I want to do is I just want to hold up and sort of change screens for a second, make my summary, and then move on with the next questions, which I will do here. Yeah, here we go. Right, so for me, significantly looking different electrodes, but actually at the molecular scale, the molecules don't really understand the difference between the circular and the rectangular. It's really because these are kind of macro scale electrodes, not on the micrometer scale, when you may start getting microelectrode type responses. So what I'm going to do now is go back to my presentation, do a summary on that question, and move on. So just so you know how I did that work there, this is the settings that I just used, and I did it on our rectangular electrode, which is the 303, and I also did it on our circular electrode, which is the 501. If you do have any questions regarding ZP screen printed electrodes, don't hesitate to reach out to us. What I will say as well is that I will make a point of putting links underneath the video. Now tonight is Saturday evening, it's the 18th, but Sunday morning I'll probably put the links underneath the video. Question number 4, yeah, good one, glucose in sweat. Okay. Wearable biosensors. What I've just been doing actually is I've actually really been doing point of care diagnostics here, or when we're using screen printed electrodes, we're talking about point of care, point of need testing. Now I'm starting to transition over to wearables. I really think we're very lucky actually studying electrochemistry or working in the electrochemistry field at this moment. Electrochemistry is the ultimate science between the real world of chemistry and biology and the digital world in which we operate. In fact, that demonstration, I just took ferricyanide, I measured the chemistry of it, and the chemistry is now digitized and up in the cloud. Electrochemistry is such a good science. It's the science now of actually between the biology and chemistry world that we live in and we operate in, and the digital world in which we basically do our business in these days, and our, our data science, etc. So let's get on to wearables. We're talking about glucose in sweat. At ZP, we're very dedicated to our wearable biosensors. A couple of willing volunteers here this is at the ZP facility. Got our own gym where we do sports applications, etc. I did talk last week about ZP has a glucose sensor. I also talked about last week that ZP has a sweat patch. But I have to absolutely say, if you hear me talking with confidence about making wearable biosensors, if you really are in an academic position and you're buying, technology off us, you're really only able to achieve TRL 3, technology readiness level number 3. Again, BioLink is a good data point for you. 154 million raised in the last 4 years. I can think of there's a company in Australia as well at the moment doing microneedles, also having to raise lots of money. It's very hard to do wearable biosensors, so you've got to set your expectations. With that said, we do sell technology on the website. I just want to give you some sense of that the signals may be very noisy. I know because we do this kind of work, but they are asking, can we measure low glucose concentrations in sweat? Well, of course, the first question I might ask you is, what is the concentration of glucose in sweat? There's literature on this, but actually, there's never really been. There is one company at the moment in San Diego trying to do glucose in sweat, but that's probably one of the first attempts of commercially trying to do this. So how reliable is really anyone's knowledge on glucose in sweat? It's actually a little bit questionable until somebody's poured in millions and millions of dollars into this. The scientific papers, you'll probably find some discrepancies in the literature, but I will talk about that. How long can the sensors last for? I'll show you half a year's worth of data. Do you need a reader? I'll show you with a reader, and we can bundle it together. Now I'll probably put some links underneath this video afterwards to sort of try and make a landing page with if I can call it an academic bundle, where I try to put the sensor, the sweat patch, the electronics, and the test solution together. But again, if your budget's limited and you're just working on your own, you will only be able to bring it to a certain point. And I would say TRL 3, technology readiness level number 3. I did go away and try and look up what the kind of glucose expectations in sweat was. So it's about 0.1 to 1 milligrams per DL. So we at ZP probably could use our glucose sensors to do this. But that's because we are very good in the way we do our work. And I'm not criticizing anyone, but just understand that sometimes whether a sensor behaves well is very actually dependent on the scientists themselves. The scientist is very much part of the experiment. So when I look at our signal, this signal here is 90 megs per DL. So I appreciate that, I have to kind of, sort of imagine, can I detect 1/100th of this? I'm not going to make too many statements, but I would be confident that we can. But that doesn't mean that somebody else whose lab setup is not as elegant as ours, or their instrumentation is not as good as ours, or something like that, could actually do it. So we could, but I can't make that blanket statement that everyone could. It depends on your engineering and your science. The sensor will just last forever unless you really, unless glucose sensors are very robust. That's all I can say about it. Some people do manage to break them, but inherently they're actually quite robust and can last a long time. Electronics wise, we have two sets of electronics. We have electronics that we use with really well-funded clients. That's what we have on the left. And then on the right, something that we do sell on the web store. But just know that we have really good electronics for making wearable sensors, but we only use them with clients internally and what clients that are working with us directly. And those are big projects. They're not on the web store. But I've linked to both of them just for your interest, and I have linked to this one, and it is available for purchase. But again, the electronics that I'm showing, the sensor I'm showing, the sweat patch I'm showing, the test solution that I'm going to show, it'll only bring you to TRL 3. It's too much for me to say that you will have an amazing success, because people put large teams and hundreds of millions into doing this kind of work. So this is the test solution as well. Again, I might make a landing page with all of this, but you'll find any of these links underneath this video but you may have to wait 24 hours for those links to actually appear. Question number 5. Somebody at ZP, we do a lot of food testing applications. Somebody was asking whether we could detect soy. Soy is used as in a lot of foods. I had a look at the marker for soy, which is this molecule called Genistein or Genistein, and it is electrochemically active. And the closest I've got at the moment is capsaicin. So I just but capsaicin, I know that for non-chemists they say, well, those molecules are very different, but they're actually not that different. The electrochemical functionality, there's OH here, there's OH here, there's OH here. This also has an OH as well. So they're capsaicin and genistein are actually similar enough for me to make that claim that, yeah, we can detect genistein. What I want to do, I was just going to do a quick demo actually of measuring capsaicin, but I just laughing because somebody sent me this evening. This is Ed Curry. Ed Curry has grown what's called Pepper X. It's the world's hottest chili. He's a good guy. I think he's a really honest. Well, he comes across very well. A real straight shooter, I would say. But I was laughing because when I looked when I was looking at the video, I saw one of our boxes in the background here. So there we are. We're famous. We're on Ed Curry. So Ed Curry is the Guinness World Record holder for growing the hottest chili. He did actually grow Carolina Reaper, and now he grows Pepper X. And I just noticed one of our boxes in the back of his store there, so I thought that's quite sweet. He's obviously got some of our technology. With that said, I'm going to do a quick demonstration actually. This is why this is such an elegant little potentiostat, because what I'm going to now do is, you saw me do a couple of cyclovoltammograms earlier on. Now I'm going to use the same instrument to actually make a measurement on chili. So let me just flick that out of there. Let me just grab some chili sensors. Those are not chili sensors. So let me just grab some of those. Yep. Right. So I'm going to put this on here. So I'm using the capsaicin as a surrogate for genistein, but both molecules are similar enough from an electrochemistry perspective that we can do this. So I'll just label that up. I'll go like that. I'm doing everything live, so sorry if I'm sort of... Right, grab a pipette tip, grab a sample. Yeah. It doesn't mean that this... Yeah, well, I'll just do it and see what we get. Okay, so let me grab that. Again, love it. 50 microliters is all we need. This sample, by the way, is not like amazingly pure or amazingly filtered or something. This is the beautiful thing, again, about electrochemistry. You can actually take on quite dirty samples. But I've got the sample on there. I'll go to here. I'll go start, and off it goes. You may notice something actually, that ZP, we do try to make our assays quite quick. It's funny, I was talking about that experiment earlier on where somebody did a 1,000 millivolts per second. We would actually... It's actually too concentrated, but I'll show you what the data looks like. But the reason that we like to do our assays quite quickly is because people, want results. People in the real world don't want to wait, whilst you do an experiment at 10 millivolts per second or 1 millivolt per second. No, they actually want results really quite quickly. Now this says it's actually upload complete. It actually says too high, dilute more. What it means is there's so much capsaicin in that sample that it actually wants me to do a bit more of a dilution, but it doesn't stop me doing the demo which I wanted to do. So what I'm really like about this is actually we've got quite a bit of AI built into this system as well, and it's actually analysed the data. So let me just show you what the system's actually done. So I'll just go to my screen. I'll just do a refresh. Hey Martin, where's your data? I don't need to ever wonder where my data is. There it is. It's in the cloud. And I'll just have a quick look at this signal. Yeah, not too bad actually, but what it kind of considers this peak a little bit too high, but we've sort of trained the algorithm. Maybe the algorithm's a bit too sensitive, but it's quite sweet because it's actually come back and given me a Scoville heat unit of 124,000 Scoville heat units. Look at these beautiful voltammograms. This is the peaks for capsaicin admittedly, but in answer to the question, can we build a system for doing Genistein? The quick answer is yes, and really no problems. We've got the sensors, got the technology, you've even got the cloud system, and it's, you know, it is something that's well within our capability. So question number 1, gold PCBs. This is something I've definitely been working on for the last 15 years. You definitely will have corrosion. You never said it in your emails, but I got a super strong suspicion that you will. Thickening up is something that, you know, is the most obvious thing to try. If you do try it, you will find it'll probably fail. I'd be very surprised if it doesn't. Massius or think about screen printed electrode golds. I mean, PCBs is not really, it's not adding a lot of value. It's causing you some problems. Geometries of screen printed electrodes. Yeah, we've got geometries where we've got circular electrodes and we've got rectangular electrodes. But on this millimeter scale, we're not getting those kind of edge or corner effects that you may think that we were getting. Sometimes we have rectangular shapes, sometimes we have circular shapes. These have come about for particular needs that we may have at any one time. And you've seen me try both electrodes this evening. Now, a particular client has got a problem with a capacitance on their voltammetry, but they are using 1000 millivolts per second. When I was just doing those 2 experiments there, I didn't have that capacitance effect, and I'd only dropped it down to 100 millivolts per second. So dropping that down would really help. Glucose and sweat. I'm only just trying to set expectations. I've given you a link to sensors. I've given you a link to microfluidics. I've given you a link to electronics. I've given you a link to test solution. But really do understand, you know, that companies, Dexcom, Abbott spent $1 billion getting their wearable glucose sensor to market. BioLink are not on the market yet. Have spent $154 million. You have to understand what you can achieve if you're one person with one small budget. You know, of course, try. You know, this is all fine. You know, good, but just know you've got to understand where you're at. And then Genistein, can we do it? Yes, we can. Can I demonstrate that, you know, a capability to do it? Yeah, capsaicin's similar enough that actually it does demonstrate the point. Now, if you do have any questions for ZP, please don't hesitate to reach out to us. Nice to get the questions. They're definitely stimulating, especially the one on geometries tonight. That was a good question. Appreciate it. And again, if you've got any questions, glad to receive them. Thanks so much. Take care. Night night.